Good afternoon, everyone. First of all, I would like to thank the audience who are including some of my friends joining the seminar today. And also I would like to thank the organizers who give me the opportunity to present for Hong Kong Institute of Clean Energy. My name is WU Hao. Currently is a research associate under the supervision of Professor Yin Hao from School of Energy and Environment. In today's talk, I would like to introduce my research story about artificial photosynthesis for power to X. Artificial photosynthesis is a process that mimics nature. There is no word. Sorry. Yes. One minute. Okay, good. Okay. So artificial photosynthesis is a process that mimics nature, which can convert waste such as carbon dioxide into superfuels or green chemicals. When talking about photosynthesis, actually nature has done a very good job. That's why we can see the plant on the earth can harvest sunlight and convert the carbon dioxide and water into sugar and release the oxygen back to the air. I would like to say that if there is no such natural process, our life will take distinct paths. And in the artificial photosynthesis, currently, the dominant way is using the silicon-based solar cell, which can convert the light into electricity, and use that electricity to drive up the carbon dioxide electrolysis to produce hydrocarbons and oxygenates. And in my current research, I want to develop an alternative strategy, which can combine the light harvesting and the redox reaction in one unit. How does it happen? It is mainly based on photocatalysis, in which the photoactive semiconductor can harvest the light and generate electron hole pairs. And those electron hole pairs can migrate to the surface of semiconductor and drive out the redox reactions. Many researchers are interested in doing photocatalysis because they can see it for various applications. It can be used for environmental applications, such as air purification, wastewater treatment, or the degradation of solid waste. It can be used for fine organic synthesis or solar energy conversion applications, or we call it power to X, such as carbon dioxide reduction conversion, water splitting, hydrogen peroxide generation, and ammonium synthesis. So currently, our group is interested in developing the photocatalysis process for power to X. Photocatalysis is a relatively complex process, involve multiple steps, ranging from the charge separation to the surface catalysis. The overall photocatalytic efficiency is determined by the efficiencies of charge generation, charge transport, and the surface reaction. Here, I would like to note that the time scale of electron hole charge recombination is multiple scale faster than the surface catalysis process, which is very difficult to control, but critical to the overall efficiency. That's why the manipulation of charge transport plays a critical role in determining the overall photocatalytic efficiency. Based on that, I would like to introduce the general strategies in manipulating charge transport by photocatalyst design. They are nanostructuring, defect engineering, crystal facet engineering, and band structure engineering. In the following talk, I would like to introduce how our group applies such strategies in designing our photocatalyst to achieve a better photocatalytic performance. I believe which are also no strangers to most of the audience today. So first of all, please let me introduce our recent study on the development of bismuth one-day photoanode for water oxidation, which is a very important half reaction for photoelectrochemical water splitting. Bismuth one-day is one of the benchmark materials has been widely used for such a reaction. However, its high performance is still limited by two major challenges. The first is poor charge separation, which is mainly limited by the small pore run formation. The second is poor surface kinetics, either in the surface catalysis or surface charge transfer kinetics. So we're thinking of one strategy to address these two challenges simultaneously, and we plan to modify our bismuth one-day photoanode with phosphor dopants. But before introducing this project, I would like to give a brief introduction about small pore run, which may be a relatively new term to some of our audience today. Small pore run is caused by the lattice-phonon interaction. When we shine the light on the bismuth one-day, it can induce one electron. And such electron can be confined within one lattice unit and causing lattice expansion and forming a small pore run. The formed small pore run is generally regarded as a localized band states, which require thermal energy to re-excite the confined electron back to the delocalized band states and move forward. So to better understand the unique property of small pore run, I would like to compare it with its counterpart. Small pore run, also called Hoiston pore run, is pore run radius generally only within one lattice unit, and it has a thermally activated Hawking mobility, which is much smaller than 1 centimeter square per voltage per second. And on the other hand, the large pore run, also called frothless pore run, its pore run radius generally across several lattice units, and it has a free carrier mobility, which is much higher than 1 centimeter square per voltage per second, and its mobility is generally decreased with reading the temperature. Upon knowing the distinct properties between the small and large pore run, we firstly applied the temperature-dependent conductance measurements on our samples. And we found that the bismuth-1 photoanodes with or without phosphor doping both shows the increased conductance with reading the temperature. It indicates their Hoping conduction mechanism of the sample. And if we plot their conductance with the temperature following the Arrhenius manner, we found that the activation energy for the small pore run Hoping for phosphor-doped bismuth-1 is smaller than that of the Pristin sample, indicating a better charge transport behavior. And our results from time-resolved microwave conductivity measurement, TRMC results, also suggest that the phosphor-doped bismuth-1 has a better charge mobility than that of the Pristin sample. Upon knowing that, we also applied the DFT study using the cladding-large elastic band (CNAB) method to understand the different pore run Hoping behaviors between the two samples. We found that upon the phosphor doping, it can reduce the activation energy for the small pore run Hoping of the bismuth-1. It indicates that the confined small pore run require less thermal energy to hop from one side to the next, thus contributing to a better charge transport behavior. And also, we determined their energy positions of pore run states for both samples. We found that the phosphorus doping can uplift the energy position of pore run states. It means that confined electron can be much more easily re-excited back to the delocalized band states and move forward. And this is the first time for us to report that phosphor doping can decrease the pore run Hoping activation energy in bismuth-1, which is very meaningful to the research community. And upon the mediation of pore run transport, we achieved the record high applied best photo to current efficiency of 2.21% at 0.6 voltage with RHE. And here is a video. As shown in the normal speed video, we can say that under the light illumination, our sample can show a very efficient water oxidation activity. Okay, so upon the introduction about our recent study on the development of bismuth-1 photoanode for water splitting, in the following talk, I will mainly introduce our recent studies on carbon dioxide reduction reaction. Firstly, I would like to introduce our recent study on cuprous oxide photocatalyst. Cuprous oxide is also one of the benchmark materials has been widely reported and used for such reaction. However, when we use it for the carbon dioxide reduction reaction, there are 3 major challenges that we need to address. The first is low stability. Under the light illumination, cuprous oxide can be either reduced to copper or oxidized to copper oxide, thus losing its excellent visible light harvesting ability. Secondly, it's due to the intrinsic bulk property of metal oxide. The cuprous oxide cannot provide abundant active site for the carbon dioxide absorption and activation. Thirdly, is the distributed products. The conduction band of cuprous oxide is thermodynamically favorable for many carbon dioxide reduction reactions. And compared to other products, the carbon dioxide to methane require 8 electrons of charge transfer, which is more challenging from the kinetic point of view. So we're thinking of one strategy to address these 3 challenges, and we plan to modify our cuprous oxide photocatalyst with metal organic frameworks, MOS. So we use an innovative synthesis technique of topotactic conversion strategy to put a homogeneous layer of copper MOS on the cuprous oxide surface without using any surfactant. And from the image of the real sample, we can notice that upon the conversion, we changed the original reddish color of cuprous oxide into a greenish color, which is reflected by the copper MOS after absorbing the water molecules from the atmosphere, which is a very beautiful color, just such as a green leaf. And from the TM image and the corresponding EDX lens scan results, we can notice that we have successfully synthesize the co-shell nanostructure with the cuprous oxide as a core and the copper bismuth as a shell. Upon doing that, we applied our photocatalyst for carbon dioxide reduction reaction. And we found that the MOS coating can significantly enhance the photocatalyst carbon dioxide to methane activity with around 2.5 times enhancement. And more importantly, we also found that the MOS coating can significantly improve the long-term stability of cuprous oxide in the carbon dioxide reduction reaction. To be more specific, for the composite photocatalyst on the right side, with the MOS coatings, we can retain around 70% of the initial activity after 5 cycles of identical experiments. On the other hand, for the bare cuprous oxide, we almost lost activity after only 3 cycles of experiments. Despite the improved activity and stability, the stoichiometric evolution of product is always a focus in photocatalysis. As shown in the equation on the PPT slide, the produced oxygen and methane should be in 2:1 ratio. And our results indeed shows the stoichiometric evolution of methane and oxygen during the time-dependent reaction, which is a very important indication because if there is a big deviation from 2:1 ratio, it means that the photo-induced electrons and the holes are not fully participating in the reaction. And we said that since we involved MOFs in the photocatalyst design, which is a carbon-based material, we were wondering if the produced methane and oxygen are indeed from the carbon dioxide reduction reaction. So we did the isotope experiments using carbon dioxide with carbon-13 and water with oxygen-18. The results collectively suggest that the produced methane and oxygen are not from the parasitic reaction of the photocatalyst itself. Upon knowing that, we are now in a position to understand the underlying mechanism behind the improved activity and stability. The first and most natural thought is that copper-based MOF is a very good gas solvent, which can provide enriched carbon dioxide atmosphere for the redox reaction. So, and our results also suggest that the composite photocatalyst with copper MOFs shows a much improved carbon dioxide uptake capacity than that of the pristine of the Bayer cuprous oxide with around 7 times enhancement. Besides that, we are also interested about the potential charge transport mechanism behind the design composite photocatalyst. So firstly, we did the steady-state photoluminescence, steady-state PR study on our samples. For the Bayer cuprous oxide, it shows an intrinsic emission signal, which is arising from the charge recombination of cuprous oxide upon the light illumination. Intriguingly, upon the MOF coatings, we created a new emission signal centered around 630 nanometers. It indicates that there is a potential new charge recombination process between the cuprous oxide and the copper MOFs. So if we plot the energy levels of copper MOFs together with cuprous oxide, we propose that the energetic electrons on the cuprous oxide can be transferred to the lumen level of copper MOFs. When there's no carbon dioxide existed in the system, the transferred electron can be recombined with the host on the valence band of cuprous oxide, thus generating a new charge recombination process. And here I would like to highlight that the energy difference between the lumen level of copper MOF and the valence band of cuprous oxide is perfectly matched with the wavelength value of 630 nanometer, as we observed from the steady-state PR data. To further prove such process, we also did a time-resolved PR study on our samples. We firstly monitored their emission signal at 630 nanometers. We found that the composite photocatalyst shows a very obvious signal with a significant decay. On the other hand, the Bayer cuprous oxide shows a negligible signal, and we cannot detect it. We also monitored their emission signal at 500 nanometers. We found that both samples show a very comparable behavior with a negligible difference. So the observation from the time-resolved PR are consistent with the steady-state PR data. And this is the first time for us to report that the photo-induced electron can transfer from the excited cuprous oxide to MOFs. And our study also extended the relationships between MOFs and metal oxide beyond their conventional phase disruption, chemi-sorption type of interactions to now include charge separation. Even though our current study shows improved activity and stability for the carbon dioxide to methane conversion, however, our current system, the overall activity, is still limited by the oxidation part of cuprous oxide. To be more specific, our current system is still limited by the poor transport of photo-induced holes and the limited water oxidation power. So we're thinking of one strategy to assemble another water oxidation photocatalyst of bismuth-1 with our current system to further improve the overall activity for carbon dioxide reduction reaction. But before we assemble bismuth-1, there are plenty rooms for us to investigate different properties of it and select out the best candidate. Many years ago, our PhD group published a paper investigating the highly ordered porous structure of perovskite. It triggers my curiosity to apply such structure to my own photocatalyst because it has many obvious advantages, such as large surface area, enriched surface functionality, strong light trapping effect, and the potential unique charge carrier transport. However, few reports covering the different intrinsic charge transport properties between the highly ordered porous structured photocatalyst and its bulk counterpart. For example, the carrier diffusion length, charge mobility, and the electron lifetime. So based on that, we synthesized the highly ordered porous structured bismuth-1. And from the TEM image, there are two unique factors we can notice. The first is ultra-thin and crystalline internal wall. When the size of non-structured photocatalysts narrowed down to 10 nanometer, they have been widely reported to show the quantum confinement effect. So we were wondering if our 3-dome bismuth one-day also have such an effect. So we firstly did the UV measurement on our samples. We found that compared to the ball counterpart of pre-like sample, the 3-dome bismuth one-day shows a significant blue shift of band absorption. It indicates the larger band gap. And combining with the UPS results, we determined their energy band positions of both samples. We found that arising from the quantum confinement effect, which uplifted the conduction band position, the 3-dome bismuth one-day now is thermodynamically favorable for hydrogen evolution reaction, which has been really reported in the literature. In the literature, the bismuth one-day is widely reported as an efficient catalyst for water oxidation, but really used for hydrogen evolution. So to further prove such effect, we did the hydrogen evolution activity test on our samples. We found that the 3-dome bismuth one-day shows an efficient and stable hydrogen evolution activity. On the other hand, the pre-like sample shows a negligible performance. So this is the first time for us to report the quantum confinement effect arising from the unique 3-dome structure of bismuth one-day, enabling it as an efficient hydrogen evolution photocatalyst, which is very meaningful to the research community. Besides that, the second unique factor we can notice from the TEM image is the distinct crystal plans between the interconnection part and the internal wall. In the introduction part, I have introduced you that crystal facet engineering is one of the general strategies in designing the photocatalyst and manipulating the charge transport. So to prove there is a built-in energy position gradient existed in this unique structure, we firstly applied the Kelvin probe force microscopy (PPFM) studies on our sample. We found that the 3-dome bismuth one-day shows different contact potentials on its surface. If we did a line scan across the interconnection part, the wall of the pore, and the internal wall, we found that the distance of contact potential difference, CPD, from the internal wall to the working probe is larger than that of the interconnection part. It indicates that there is a built-in electrical field with an upward band bending from the internal wall to the interconnection part, which can facilitate the electron extraction to the internal wall and accumulate the holes near the interconnection part, thus facilitating the special charge separation and contributing to a better charge transport behavior. And our results from time results microwave conductivity, TRMC measurement, also suggest that the 3-dome bismuth one-day has a much higher charge mobility than that of the bulk sample of pre-like bismuth one-day. And upon the publication of our work, we were interviewed by TVB program, which reported our work on using the photocatalysis process to decompose contaminated river water and generate green hydrogen as a clean energy source, which has a very specific meaning to the local society. And recently, as led by our PI, Professor WU Hao SEE, we secured a very competitive grant from Great Tech Fund, in which we'll build a demonstration kit using the photocatalyst panel in the Hong Kong Community Park for demonstration and educational purpose, which can increase the greater public awareness about the sustainable development and carbon neutrality in our CG University of Hong Kong. And meanwhile, our group also collaborates with electrical and mechanical service department from Hong Kong government. And this picture was showed and organized by my colleague, Dr. Ho Ying-zhong, which shows that we're using the lamp to provide the light source and generate the photo-induced green hydrogen, and use the generated green hydrogen to power up the commercialized fuel cell and provide the electricity to light up the LED bulb, which is a very interesting work. And as the final word, I would like to thank all the audience attention today. And I believe with the mutual efforts from our young scientists enrolled in the Hong Kong SEE, we can dedicate ourselves to contribute to sustainable development and carbon neutrality in the local society or even global community. Thank you very much, and your suggestions and questions are welcome. Thank you.